This video will discuss open loop control of this little motor that we have been studying in the lab. In a previous lab, we used the same configuration, an H-bridge driving this little hobby motor from SparkFun with an Arduino and Python, and characterized the motor, developed a torque speed curve. And in this video and in a following video, we're going to talk about first open loop control and then closed loop control. So these two videos cover one lab experience where we talk about open and closed loop control. We want to learn about a little bit about feedback. Again, first we'll talk about open loop control. We want to especially focus more on implementation of motor speed feedback control, especially using Arduino, of course using Python as we always do to control the experiments and also to log data. And mostly we're going to run some specific experiments depending on how much time you have in the lab according to your TA. Before we talk about open loop control in this video, just want to review the general sort of closed loop feedback control diagram, which is good to be familiar with even if you don't take more extended study of feedback. Everybody kind of has an idea of what's meant by feedback, but it's good. This is a very standard diagram. Be familiar with the elements of this. What we are generally trying to control is what we call the plant in this box here. And the plant has an input here. We're going to be calling that U. And change this a little bit. There. And that control actuation drives the output. And the output in a feedback control system is fed back. You may have some kind of a sensing system that then generates a feedback signal. And here's the key, right, in feedback control is it has a formation of some kind of an error signal, right? You have a reference, something you want the reference, if you think about it, has to have the same units, or it's related to what you're trying to control. So in our case with the motor speed, we're trying to control omega of that motor, so this is going to be a reference speed that we're trying to achieve. And that error then is used by the controller to generate a control action. The inputs into the plant might actually also have some disturbances. So I'll talk a little bit about what that means in a second. But there's obviously always things that are acting on your plant that may influence its behavior, and what a feedback control system is working to counteract those effects. Just some definitions. Again, the plant is the system that you're trying to control. The controller it can generate inputs, to the plant to achieve desired objective, and there's always specifications about how you want that, performance to be achieved and so on. And then there's a sensor that is able to measure that output signal. This shows what we call a single input, single output system, right? There's one input, one output. More advanced control systems, more complex systems, aircraft and other kinds of systems that have multiple variables that you're trying to control, not just one, may have multiple output representations and maybe even multiple inputs. So more complex control representations. Now in open loop control, where it's the way a lot of things are built, right? You don't necessarily look at the output to make changes to what's coming in. Now, what the problem is that you're then susceptible to disturbances. You're also susceptible to the fact that the system itself might change. You might think that giving it some kind of an input would achieve an output based on your study of the system, shown here in a kind of in a transfer function form. But if the system changes a little bit, right, then what you think is going to happen is not going to happen. So the variation of parameters of the system itself, right, your model might be off, makes open loop control challenging. Again, it can be good if you have a good model. A lot of systems work this way. A lot of mechanisms are designed to give you certain kinds of actions reliably and so on. A lot of timed processes have been designed this way. Again, a lot of these now modern technology has changed how toasters and even dryers work, right? There's now sensors in there that are closing the loop. But a lot of simple time processes are also examples of open loop control. And even trying to get our little hobby motor to go to a different position or to go at a certain speed, we're going to look at how we use open loop control for that. Okay. The takeaway, again, a good model can help you control behavior of something in the design. And as we're going to see, we're going to use a little bit of open loop control to help us even when we have feedback. Okay. So a couple of different ways that you can build open loop control, and focusing here on this little permanent magnet DC motor is, we can go into the lab and make measurements. And in our case, we can set the pulse width modulation. We can, we have an encoder, so we can measure motor speed, and we can build this nice little curve here. And then we've got sort of a correlation. If we want a certain speed, then we know, right, if we want this speed, we can come here, and a nice little correlation tells us what the pulse width modulation should be. This is nice and linear. It doesn't have to be linear as long as we kind of model that behavior. And again, the thing is that this curve, though, is measured for certain conditions, for as long as parameters don't change, as long as I don't have any other external effects. So as long as that's the case, then this is a pretty good way to control the system. Another way is if we have a model of the motor, say from torque speed characteristics, either from a manufacturer or from one that we measured ourselves. And here's the example of the one that we measured in the lab. And so we can set the pulse width modulation just by using the parameters that we might have for this motor. You recall the gyrator modulus, the motor constant, the damping that we might know in the motor, and the resistance. And this model could actually allow us to look at different kinds of motors and maybe evaluate different designs and how to select a motor for a different application. But we can also see by looking at these equations that we can set the input, the pulse width modulation, by finding what is the required, basically we're doing an inverse model here. What is the input voltage required to achieve a certain speed? So this little relation in step 4 here, if I set the speed here, and I've got all those constants as well as knowledge about like what the friction torque is, or even some other known loads that are on there that you might study, then look, you can determine the input voltage, set your pulse width modulation, and then you can build an open loop control. Now, what does that look like? Well, in a block diagram form, which is the way we study control systems, we're trying to control speed, right? So we give we specify, hey, this is the speed we want to go, the reference. We have some gain, open loop gain, that we can determine in at least 2 ways. One that I've already shown you on slide 6, using that correlation that you might build, or one using a torque speed curve model. And there could be other ways that you can do this. And that's going to give you your control action that goes right into your, in this case with pulse width modulation, that goes right into the, well, actually it doesn't really, I'm leaving something out, right? Should have put this in here. There's an H bridge here, isn't there? Right? So kind of oversimplified it there, but the H bridge is what receives the pulse width modulation. I'll be talking more about that when we talk more about the closed loop control, and then that sends power right to the motor. Okay. Okay. Now, how do we evaluate it in the lab? Well, you can evaluate it in a couple of different ways. One is you can just drive and measure set it at a certain speed, measure the mean speed if you have, like we have an encoder, and how well did it work? How well did using that gain work for you? The other way is you could drive it at a constant speed over a certain time interval and see what kind of displacement it makes, right? If you think about it, a lot of little robots work that way. You control the speed, and this thing starts moving. And if you know the radius, the speed, you'll know what kind of distance you've traveled. And it's a lot of times real simple models for dead reckoning and so on for simple robots. Hey, I want to travel 1 meter. Well, I can drive it control the speed. That's why you have little speed controllers. turn it on for a certain amount of time, and I can get to this position, with some error, right? So that's one way to evaluate your controller. Remember, though, that the motor has other dynamic effects that the open loop control doesn't take into account, right? So, so another way to evaluate, your open loop control, if you have a model of the motor, which we kind of do, and sometimes you build a decent model of these motors, we can add some inertia in here and build a model and run simulations using open loop control or any other control, right? We do this for all kinds of control, where we build a model, test our control that way, and we can run simulations before we run into the lab and test it, right? So we have this included as an exercise in the pre-lab for you to do with your model, run so you can understand how is open loop control implemented, what kind of results do I get, and so I'm giving you a little Python code that helps you, shows you how to run an open loop control on the permanent magnet DC motor. So that's summarized here on this slide. The first code that I give you that's on the lecture page is just a straight simulation in Python using the code that we've used before. No control, it's just here's a motor, give it an input voltage and it does something, right? Then there's another one that actually has the open loop controller implemented as we've discussed here, and it does a couple of different things. It turns the motor on and off, and also you can set the time interval so you can see, and then it'll track the position so you can see how well did I achieve a certain, let's say you figure out what, if I want to go 90 degrees at a constant speed, this is how long I should leave it on, turn it off, and let's see how well your model predicts that. If you have a pretty good model of your system, then you can see how well that control works. Okay. Again, it's all in the spirit of studying open loop control. And here's first the simulation of the motor, just on simple on off. Again, we always create a nice little set of equations. Here the state equations that you've learned to build in 344. There's one for omega dot, can't see that, but omega dot. There's one for theta dot. Those two equations there. You turn it on and off. It sets the input voltage as just the battery voltage. There's no H-bridge model here, and then it just computes, and again the code computes using RK algorithm the states, and then also computes the current and the input voltage you put in. Okay, so that's one little code you can play with, and things will look like this. Look, I turned it on and off, and what it did is the current peaked up, went to steady state, peaked down to turn off, and then you can see that the speed kind of went up, kind of takes a little bit of a transient because it has some inertia and resistance, and then when you turn off it drops down, and then here's how the angle goes to a desired position. Okay. The other example I gave you with the open loop control is a little different. It uses a model of the torque speed curve model, and you can put in the parameters for your particular motor, and as you can see here, you can turn it on and off, and you can set a pulse width modulation. Here I'm using MCC to set that, and then that MCC can be used with the battery voltage to set the input voltage, right? And that's using a really simple model of an H-bridge that says if I have batteries here, and I'll show this some more later, and I give it a pulse width modulation input, it sets the average voltage here, and that's kind of a rough, nice, simple little model of an H-bridge that you can use in these simulations, and you can play around with that. Right. So this little model, right, this open loop control, by the way, here I'm using the torque speed curve, but you can also use the open loop gain to set your pulse width modulation, either PWM or MCC, and that's exactly what you're going to do in the lab. Right, so here's a little snippet of code from the Arduino code that we're going to give you, and you can see you're going to be setting a reference speed. You're going to take whatever open loop gain that you've determined, maybe by playing around with simulations or from direct measurement from torque speed curve, and then that's going to be set in your pulse width modulation to send to your Arduino, and you're going to evaluate how that works. All right. First time I did this, played around with this, you can get pretty good relationship between simulations and experiments. I mean, this shows up here the simulation open loop control versus what I measured off of the Arduino, and it's pretty good. You can get, for this simple system, you can get pretty good correlation there. Okay. And I also, on my motor, I attached a little shaft, and I watched it turn. I said, hey, I want to go 180 degrees, and I was off because I was using when I did this back in 2020 or so, I was using the wrong gear ratio for this motor, which is 48 instead of 45. Okay. But you can, again, this is a neat way of checking, hey, how good is my speed control? Let's say if you're not measuring speed, I can, by inspection, you can see, hey, I went 180 degrees. Hey, my speed control is working pretty well. Okay, just to close up this discussion on open loop control, again, want to prepare you for the lab, study open loop control simulation. That helps you kind of get it in your head. You can either use torque speed curve or you can use a correlation. And we have a nice Python code that's actually going to run both open loop and closed loop control. I'll talk more about that in the next video. And the TA will help you understand how to run that code and everything. And I'll close this up. In the next video, I'll talk more about closed loop control and PID.